if f of z is bounded in the punctured ball for any r bigger than 0, then removable. Actually, this is an if and only if. So f of z is bounded in the punctured ball is equivalent to z0 is removable. Because if it is removable, then for sure that's true. Yeah? For sure that's true. Because once we remove the singularity, then we have something holomorphic. So in a small ball, for sure it's bounded, so that's definitely true. So that is the first kind of singularity. The second kind is that if the limit as z goes to z0 of the absolute value of z0 equals infinity, this is equivalent to f has a pole. That's at 0. And then what's left, if neither of these things true, I guess it's I before E. Then it's the only other thing it can be, it's an essential singularity. And if we think about the example of the essential singularity we thought about, it was this, right? Yeah? So it definitely wasn't the case that this thing remains bounded as z goes to 0. We saw that, right? But it's also not the case that this thing blows up to infinity. If we approach 0 along the complex numbers, then this thing just went spiraling round and round 0. Yeah? Remember this? Yeah? So we have three kinds of singularities. We have the singularities that essentially are not there, where in some neighborhood around the point, it remains a bounded function, and then nothing's actually happening there. It's a false singularity, it's a removable singularity. It's something like z squared minus 1 over z plus 1, right? This thing is removable. Removable singularity at z equals 1, minus 1. Right? A priori, this thing isn't defined at minus 1. Yeah? But just some algebra, we know that this thing is equal to z plus 1, z minus 1 over z plus 1. Yeah? So then this thing actually is just equal to z minus 1. Yeah? And at this minus 1, we therefore just need to define this to be equal to this thing, which is minus 2, and we've removed the singularity. Yeah? So there's no real singularity here, it's just the way somehow our function came out. And we basically don't have to worry about this kind of singularity. Yeah? Or we have a pole where it's doing something pretty uniform. It's blowing up towards infinity, and it's blowing up towards infinity in a very understandable way. Yeah? Whatever the order of the pole is, it's blowing up like absolute value of z to the n, if n is the order of the pole. Yeah? Yeah? Or we have these crazy guys that don't do either of these things. They behave in an insane way. They don't actually blow up or remain bounded. They do some combination of the two. So this is the prototypical example. This is the prototypical example. Yeah? Cool. All right, so let's prove a theorem about essential singularities. This theorem comes with a name. It is Weierstrass. Casorati, something like this. Weierstrass. I don't know how to spell this. All right, so I'm probably misspelling these names, but these are Weierstrass, of course, you've heard of. All right, so suppose F has an essential singularity at Z0, then for any r bigger than 0, the image of the punctured ball around Z0 closure is the entire complex plane. Yeah, it's the entire complex plane. Okay, so that says that if we take any little ball around our singularity, then this thing is completely covering the entire complex plane. You know? So it's wildly expanding and covering up the space. There's actually a stronger theorem by Picard that every single point in the plane, complex plane, is hit twice, except for, not twice, it's hit infinitely many times except for one point. So it is wrapping around the complex plane infinitely many times except for one point which it misses and only hits once. Not once, but it doesn't hit infinitely many times. Yeah? So this is dramatically bad behavior. Yeah. I mean, if you remember your multivariable calculus, the image of a ball, its area is something we can calculate, right, with this change of variables formula, right? So typically we could integrate around the Jacobian in the domain to get the area of the image. Yeah? But since the area of the image is infinite, that means that the Jacobian of this thing is infinite. It's incredibly expanding, or the integral of the Jacobian is infinite. It's incredibly expanding space. Yeah? So this is dramatically singular behavior, so proof. Suppose this is false. So there exists some, zeta belonging to the complex numbers, take away the closure of this thing. Yeah? That means that there's some specific distance between zeta and anything from the complex ball, because this is the closure, right? So this is an open set, so we can put a little ball around zeta. Yeah? So for some we have actually that there's a ball around zeta which is inside the complex plane, take away the closure of this thing, again, just because this entire thing is an open set. Yeah? So, consider the function say h of z, which is equal to 1 over zeta minus f of z for zeta inside this punctured ball. So, tell me cool things about this function h. It doesn't blow up, right? Why not? It's more than never equal to z. There's some distance, right? So the gap between, or the distance between zeta and f of z for any z in this punctured ball is at least delta. That's what we know, yeah? So the absolute value is less than 1 over delta by construction, because this thing is always bigger than delta. Yeah? So tell me other cool stuff about our function h now. What about h at z0? What is z0 for h? Is h defined at z0 when I just do this? Given our hypothesis, if I just ask you what h of z0 is, can you give me an answer? F has a singularity at z0, so we can't give f of z0 a value, right? So h is defined out of f, so a priori we can't say, we don't have a value of h of z0 yet. Yeah? So that is exactly what we mean by singularity. It's something where it's not defined yet. But we've got this property. So, tell me cool things about h then. What kind of singularity does h have at z0? Start again. Does it have a pole at z0? So we've learned about singularities. We've learned there are 3 kinds. Let's just list them off. Huh? What would happen if we have a pole? What would you expect from h if it had a pole at z0? Yeah, if it had a pole, then this thing would blow up as z goes to z0. That's what we just learned, huh? So does it have a pole at z0? Yep. Yeah. So it can't possibly have a pole because it's bounded. In fact, this property being bounded as we approach z0 is exactly necessary and sufficient to be a removable singularity. Yeah? So h has a removable singularity. At z0, and that gives us this bountiful extra good stuff that we can think of h as just being holomorphic. So think of h as holomorphic. In the actual ball, not the punctured ball. Okay, cool. But then if h is holomorphic, we can change things around. Let's wrap this around. We have this is equal to 1 over h of z, which implies that f of z is equal to 1 over h of z plus zeta, like this. Yeah? Cool. All right, so now, what is going to happen as z goes to z0? This zeta is just a constant, right? So we don't have to think too much about that, right? So when z approaches z0, what happens to f is really depending on what happens to this thing. Yeah? Okay, so what are the possibilities for H at Z0? Could H of Z0 just be some number? Is that possible? Some non-zero number. Why not? Yeah, no, if this thing was just some non-zero number, then as z goes to z0, then f of z just goes to 1 over h of z0 plus this zeta, which is just some number, so it tends to this limit, it's not blowing up, yeah? No. Okay, so could h of z then have a, could h of z0 therefore be 0? Okay. Jaime, you're doing lots of good stuff. Answering many questions. Can someone else explain why no? Why can we not have h of z0 being 0? Okay, and why is it the case that we know that it's going to infinity? H is what? No, it's not to do with continuity. So, oh, I take that back. Actually, continuity is enough. Continuity is enough. Yeah. Yeah. So since it's continuous, as we let z get closer and closer to z0, then h is getting smaller and smaller, so this is uniformly blowing up. Yeah? Cool. Cool. So continuity is enough. I was about to tell you the fact that we know the zero is of the form z minus z0 to some power is what we are using, but we don't need that actually because we've proved this result that blowing up to infinity is equivalent to having a pole. Yeah, so it's enough that it's continuity. Good. So this limit would be equal to infinity. So a pole. So neither of these things are possible because by hypothesis we have an essential singularity. Therefore, what does that mean? That means there does not exist any zeta which is inside the complex numbers take away the closure of the image of the ball. Huh? So this is indeed a crazily badly behaved function as we approach z0. This is wild behavior. And this is showing that this behavior that we looked in some detail of this function e to the 1 over z is somewhat generic. If we keep playing with that function, we'd see that it really does have that property. It's wrapping around the entire complex plane just in any small neighborhood of 0. And that's what any essential singularity does. So when we have a bad singularity, then it's really bad. And if we don't have a bad singularity, then we have actually really rather good singularities, rather manageable singularities, either removable singularities, which we can just forget about, or poles, which are extremely regular and controllable in the way that they are singular.